Today we looked into this clustering. Today also I am going to cover one more way of doing clustering. Right, this is mostly pre-processing technique kind of clustering, I would say. Okay. So DBSCAN. DBSCAN is a algorithm. Give you one. DBSCAN is an algorithm, density-based spatial clustering, right? So DBSCAN applications with noise. Okay, so um, name is not that important, but DBSCAN, people call it as DBSCAN. This is very simple technique. Right? There are two core concepts as epsilon neighborhood and core instances. Okay, epsilon neighborhood is nothing but the samples that are epsilon distant from the instance are known as epsilon neighborhood. Okay, and core instances. An instance, right? One sample with at least minimum samples. Right? There is a parameter in DBSCAN called as min underscore samples. If you specify min underscore samples is equal to 10, any sample that has neighboring samples with minimum epsilon distance, 10 minimum 10 samples are there, then you call it as core instance. That instance is called as core instance. Let me draw this and show you. It is very simple. So suppose that that's an instance. Okay, that red dot is an instance, and I said min samples is equal to 10. If I say min samples is equal to 10, right? Epsilon is equal to maybe 0.01, some number. Okay, some distance I gave, right? If I have minimum 10 samples around it, I call this instance as a core instance. Okay, and basically this whole thing is called as core instance. Sorry, not just one sample. This whole thing is called as core instance. Now with minimum samples, it's in its epsilon neighborhood is called as core instance. Okay, and there are right another one more core instance, right? One more core instance. One more core instance. Like that, I have taken many core instances there. Okay, a cluster, a long sequence of neighboring core instances is called as cluster. So you can consider this thing as a cluster and this thing is another cluster, because there are three core instances which are neighboring to each other. Right? There are two core instances neighboring to each other. So epsilon neighborhood, the samples that are epsilon distant from an instance are known as epsilon neighborhood. So if you take this dot and all these data points which are close to it are all epsilon neighborhood. If you take this data point, all the close instances are called as epsilon neighborhood. Core instance, an instance with at least minimum min samples in its epsilon neighborhood is called as core instance. So any data point which is having that epsilon neighborhood is called as core instance. A long sequence of neighboring core instances is called as cluster. Right? Neighboring. So we will specify these numbers. These are hyperparameters or parameters which we will specify and try to find out. I will show one example now. Then you will understand better. So a core instance with no neighboring core instances. So if you take another data point like this, another core instance which is very far from the other core instances, right? Then you can call this as a anomaly. Okay, anomaly or an outlier. Okay, anomaly or an outlier. So this is clear, right? Can I move on to the example?
Yes, sir.
So we worked with one of the organizations where we had to find out number of threads in a cloth. Okay, let me show you the. So this is the cloth. This is the image of a cloth. Okay, and then there are different images there, different cloths, different images. Right? We need to find out number of threads. So how did we do this? Is first we tried to convert this into a grayscale image, or for for teaching purposes, right? I did not do that, but we converted this into grayscale and then tried to apply manually the DBSCAN algorithm. Okay, manually DBSCAN algorithm. When we applied DBSCAN algorithm, right, the pattern actually changed to similar thing. Right? We were trying to bring all the images data distribution into similar thing. Right? That's what we were trying to do. So in that process, we converted the text, converted these into um, black and white, and then we applied DBSCAN and tried to give same color to similar whatever similar color we try to give same same whatever. Let me show you that example. This is the original image, right? This is the original image, and after applying DBSCAN, so applied DBSCAN with different parameters. If this is a epsilon 0.005 and the core instance size, right, 400. Epsilon and min samples is 400, epsilon is 0.005. Right, with that, right, it actually couldn't find the pattern properly, right? With the epsilon 0.005 and core instances the uh, min samples 450. See, there it is, with 450, it actually identified better, right, that, horizontal and vertical, whatever, right? It's actually forming the patterns there. And on the next image, also we tried to apply. This one actually came well. See that here, it is actually showing the horizontal and vertical lines. So we can count easily, right? If we can convert all the images, that was an experiment we did. If we can convert all the cloth images in this pattern and then convert it to grayscale, or no, convert it to grayscale and try to find this kind of a pattern, then we will be able to count, right? Using using a CNN or whatever that image processing models, we can actually count. Now how will we count? We will be doing a horizontal bounding boxes and vertical bounding boxes, and I'll explain when we actually see the CNN models, right? I'll explain that. So we tried this way. Okay, so DBSCAN is the algorithm we used to do pre-processing. It's a manual process. Every time a new cloth comes in, a person need to convert that into this kind of an image and then convert into, pass it to the model, right? Same parameters will not work for all the images. See this 0.005 and 10 is the min samples. On the previous image, 0.005 and 450 was the number, right? Here we can see a little bit of pattern, but here it got distracted, right? So the sample data collection should also happen properly. So there are two different patterns here. If you see, There are two different patterns. When a person is taking a picture, they should make sure that at one place only, with one color only, they should be taking the picture, right? So we should build, there was a big, huge requirement. We couldn't finish that project. We couldn't take up that project, because budget constraints, and it was for government, and they were asking for us to do it for free. We couldn't do it. So they have to, if we have to build a model to do whatever, right? To count the number of threads in a given area, right? Maybe a centimeter, square centimeter, or square inch. We need to build a mobile application which actually shows the user that whether the picture is taken properly, picture you are taking is appropriate to the model or not. When you put the camera of the mobile phone, right, it will actually need to specify which area should be taken. Right? So when we thought of giving a green color in the boundary where the area is correct. So here the patterns are different. If we try to apply DBSCAN, it will become like that. Okay, so here different pattern here, but when we convert this into black and white, right, we may get some, um, some similar pattern there. Okay, so this is an example of DBSCAN where you will be using it to do pre-processing, image pre-processing we can do. Okay, any questions here? How to do that model and how to run the code and all that I'll show in a minute. Any questions theoretically?
So how do you know that where we need to apply the DBSCAN?
This is one example, right? When how to know?
Yeah, for example, I got some images.
Uh,
How do I know that which one I need to use, which pre-processing I need to use?
we will try all. Basically, it is all trial and error only. You can apply k-means clustering and find out how many number of clusters are there. But yeah, there is a difference here. So if you apply k-means clustering here, you will know how many clusters are there, how many different colors are there in this image. But you may not be able to apply single color to one particular pattern, right? Maybe we can, no, maybe we can. My statement is wrong. Let us see the code, right? How I actually converted this original image, right, this original image into this kind of an image. You see this, right? This whole area became red, right? And if you see in the bottom, right, some area became white and some area became red. See that? This one. Another one. See that? There is a single color to if you look at this image, there are different shades. Right? Here there is some color, here there is some color, right? There is some black color, right? There are different shades here. But when I applied DBSCAN, right? After applying DBSCAN, after finding the clusters or the core instances, I changed the color of the core instances to one color. Right? I found different pattern, different clusters in the image, and then took the cluster and changed the color. I actually made it to two colors or three colors or something like that. There may be different colors in this. Each color is a cluster. Each color is a cluster. If you see this is a cluster. This is a cluster. Right? This is a cluster like that. Okay. So let me show you the code, and we may understand a little. My idea it is. So I need to. So in scikit-learn cluster, right, there is DBSCAN, and then I have taken this image and just showing image show, IM show, and then I reshaped this to 4 columns, and I don't know how many rows it actually takes. Okay, I converted that image to this many rows and 4 columns. So now I am applying DBSCAN. So I created a DBSCAN object with the epsilon is equal to 0.005 and 500, and then fitted the data. This image I fitted, and now I have got core sample instances. So how many core sample instances are there in my data? This many core sample instances are there. Core sample instance means an instance that has got many epsilon neighborhood this thing neighborhood neighboring samples are there. Okay, there are 1,21,031 core instances are there. So how many labels are there for these core instances? If multiple core instances are together, then we say cluster, right? If multiple core instances are together, then we say one cluster. So the algorithm would have assigned for all these 3 core instances one number, all 2 core instances another number. If you look at this data, there are 5 core instances, 6 core instances, right? Overall, it would have assigned 3 labels only. Like that, there may be 1,21,000 core instances, but overall it assigned 0 to 18 cluster numbers. -1 will be assigned to the outliers. If it finds the uh, if it finds multiple outliers, right, multiple numbers will come, -1, -2, like that. Okay, so here I was trying to see the indexes of the records which have been assigned a label -1. Okay, so in NumPy there is a method called as argware, right? Argware. Now if you see dbscan.labels underscore, there will be 1,21,031 numbers. Let me execute this. Give me 1 second. It may take some time to execute. It may take a little while. Yeah, done. Give me 1 second. Is done, right? So now you can see 4 instances, and then if you see the labels also, Oh, okay. For each instance, there will be a label, right? For each instance, there will be a label. When you do clustering, what happens? For each instance, there is going to be one label, right? So out of all those labels, we try to look at unique ones. And there are 18 clusters and one outlier, right? One outlier. So I wanted to see for which all records the label -1 is assigned. That means the outliers, which all records are outliers. I wanted to see. So argware is a method which actually takes a Boolean expression and tries to find out the index of that, the place where this condition is true, right? Argmax is going to get you the index where the value is maximum, right? The argware is going to get where this condition is true, the index of the place where the condition is true. So there are many, right? So now what I did here is in this loop, so I have taken all the unique labels, okay, and then first index of the label. So wherever that first label is found, in argware, what you get in argware, label underscore is equal to label means if you take unique labels, this is going to be -1, right? If you see unique labels, what is this? The first one is -1, right? So you came here, you said argware, right? DBSCAN dot labels underscore double equal to label, I said. That is -1. It's going to get all these indexes where the label is -1, right? Outlier. Okay. So I'm going to take minimum of it. So that's going to be 23. Okay, minimum index I have taken. Okay. And then I'm just printing, right? I'm just printing here that which index is being changed to which, right? And then what I did is I took the DBSCAN label underscore is equal to label, right? What it does, this filtering, right? On a numpy array, I took a label underscore is equal to label. That means it is going to bring out all those records which have got -1, right? -1 as the cluster, and then take the value whatever is present in here and update it. Right? X of first index label is what? X of first index label is what? I have taken the original image, right? I converted that into -1 comma 4, right? So every row will have 4 numbers. What are those numbers? Something belonging to this color, right? Something belonging to this color. A square, I think image shape. See this? This is actually, why did I convert it to 4? Because it's a 4-dimensional matrix. So there are 645 rows. Sorry. No. It is 656 by 4 matrix, and there is a depth of 6,645. So I took this 4 as the dimension and tried to convert it. There are going to be 4 numbers, 4 pixels, which belong to some color here. Okay. So I took that color, right? Those 4 pixels, and updated the original matrix. So what I'm doing basically is all the records belonging to -1, I am trying to update it with 4 numbers. All the records belonging to 0, I am going to update it with 4 numbers. All the records belonging to 1, I am updating with 4 records, 4 numbers. All the records belonging to 2, I am updating with 4 numbers. That means I am changing the color. The original image, right? Even though there are different shades, it actually identified that whole thing belongs to one color, one cluster. So for one cluster, I am assigning one color this way. Right? There are 19 colors here. Only 19 different colors. Okay. So if you want, right, you can actually do further, uh, further analysis, and you can even change the color to maybe 2 colors or 1 color, right? 2 colors or 3 colors maybe. 2 colors is more important, because we need to identify or count the threads right here. How many threads are there? So we need to get some kind of a pattern, the horizontal and vertical line pattern. So I am trying to change my image to get into that pattern so that a program, a computer can understand, how many threads are there. Got it? Did you get this logic? What I'm doing here? Did you guys get this logic?
So basically, you are trying to give some unique number or code to each of the
Each,
detectable colors.
yes, sir. Yes. I am trying to give same color to one cluster.
Sure.
I'm trying to give same color to one cluster. That way, this is my thought process. Basically, I looked into the data and I thought DBSCAN can actually change the picture into a way that makes the computer easier to understand the horizontal and vertical lines, right? So we never completely did this project, but I'm just showing you whatever work we did as part of preliminary analysis. Okay, so that is the thing. So DBSCAN can give you, this kind of, you know, especially in this kind of, in this kind of data set, right? We may have to apply DBSCAN only because um, um, identifying for the k-means clustering, it may become difficult, because there what we are doing, we are trying to find out the cluster centroids we are moving, right? So on this huge data, if you try to apply k-means clustering, it may hang. Try to do k-means clustering on this image, on this data, and see what happens. Maybe experimentally try to do that, right? So DBSCAN can actually do, can actually find, less number of clusters. If you do, the k-means clustering, right, it will not find 18 clusters. It will find more than that. Okay. So that's how I converted, right? And I tried to take, different sets of epsilons and min sample lists and tried to run, but I got out of memory error. Okay. And then I kind of reduced it to one set and then ran it. So the biggest problem with DBSCAN is it gives out of memory error. So there is optics, another algorithm which is similar to DBSCAN, but it works with huge data. Okay, I tried to do optics and run with different combinations here. So epsilon one number and min sample is different, and then in a loop I actually tried to do this. Okay. Whatever the activity I did on the top, right? The same thing I did in a loop with different combinations. Okay, epsilon one number and min samples another number. Epsilon one number, min samples another number. When I tried to do it with DBSCAN, I got out of memory error. Optics actually, there is an optimized version of DBSCAN, which has got similar parameters, but you can choose metric, Euclidean distance, cluster method DBSCAN, algorithm ball tree, right? We actually looked into that ball tree and that KD tree, right? Ball tree, there was one problem for us, right? That
So one question says here metric you said Euclidean distance. So wherever you are taking epsilon, which is nothing but a distance related metric, it is of there we're going to calculate the Euclidean distance. Is that so?
yes, sir.
Yes.
Euclidean distance less than or equal to this number.
Sure.
All those neighboring records will become one core instance, right? And then those core instances form a cluster. Many core instances form a cluster.
Sure.
So that is, DBSCAN. Have a look at it. Right? If you have any questions, right, we can look into this. But now, Narayana asked a question, right? So when to use DBSCAN, when to use K-means.
Yeah, at
So,
least my understanding, I have some understanding what I'm thinking. I know probably I may be wrong.
yeah,
So particularly here, the requirement is to measure the number of threads.
yeah,
So here, at least in this example, whatever you took,
yes,
sir.
yes, yes.
When we need to measure the number of threads, we need to see which are close to each other or which are in a sequence, and I think those kind of things.
Yeah,
So the closeliness is what we need to really identify and then make count of that.
yeah.
So maybe this is the right method to get that the closeliness.
Yeah,
That
even I thought that, but theoretically how to explain, that's what I'm thinking. I think in k-means clustering, we were actually trying to randomly assign the cluster centroids, right? We need to decide that number, right? So we should start with 1, 2, 3 like that, and then try to iteratively do that. But here, if you specify, if you take this and then specify the epsilon and the minimum samples, it is finding the number of clusters. That's the advantage here. That's what the answer I am trying to find. The way there is, you need to decide the number in k-means clustering, right?
Yeah,
Okay.
another thing which I could think of, sir, in case of the k-means clustering and all that particular application, it's very randomly distributed here, the
Yeah.
data. The location of the different points or data points and all, it's very randomly. It's
Yes.
like a sequence, and here the requirement is to count number of threads or whatever it is, right? So they are a little bit ordered here.
Yeah. Yeah.
So from that point of view, this may be better one. I'm just making a guess, sir.
Yeah, this is better. This is definitely better. I chose DBSCAN because it is better, and I forgot why I chose, and I'm just trying to think and answer there. So the first answer is that no, Girigar is actually getting it, but no, the first answer is that you can play with this epsilon and min samples, with which you can actually find the closest closest data points there. But in k-means clustering, right, you need to specify the number of clusters, but we don't know how exactly it is going to come out, right? How many clusters it may find, right? So, but when it finds clusters, right, that may not be useful also, right? You may not be able to give same color or similar color to the similar images like this, so similar areas like this. So when you want to find patches in an image, then DBSCAN is the best algorithm. So we are actually going to start another experimental project where we need to identify a car, whether it met with an accident or not. Okay. So when a car meets with an accident, right, and somebody is trying to sell a car, and the person who is trying to buy the car should know whether the car was met with an accident previously or not. So there may be a painting on a particular area which is not given by the which is not the painting done by the original company, right? It may be tinkering guys did that painting. We should be able to identify that difference, right? Where that painting was done, the original painting was there, and where is the new painting. That's a very difficult project to handle, but we'll do some experimentation there. You got the problem, right? There also maybe this is useful. Maybe. Did you get the problem? Problem statement.
Yes, sir.
So it is very difficult, right? When you get a denting work done and painting is done, you cannot make out where the exact color change is happening. There will be minute difference between the original color and the new painting, but the AI system should actually find out, whether there is any difference. Now we'll get 360 degrees photos of the car from outside, and then we need to identify it, right? Identify. That's the problem statement. think about it. Maybe, maybe by the time we reach to our deep learning, right, we'll start that and we'll have some images also. Maybe we can work on that. We are actually trying to analyze, the requirements now, and I may get pictures of maybe 10-15 cars in next couple of days. I'll show that also. If we can make out the original paint and the new, right, whatever the after repairing paint with naked eye, most probably we'll be able to find out. But if it is not, then we'll be in trouble. So I'm just thinking, how to solve that problem. Okay, so maybe we'll work on that as a project for the CNN, DNN, right, computer vision, application. Okay, so these are all experimental things I did, and you play with this and see what you can do. Or maybe I was actually trying to explain how I solved it, right? So I initially tried to convert these images into black and white, and then tried to do the DBSCAN, and first apply DBSCAN and then try to convert it to black and white. So which way it is actually, ultimately what we want to do is we want to bring all these colors, all these pictures into similar pattern. Then we want to build a model to count the threads, or to see whether it is a hand loom or a power loom. The power loom will not have this much gap, right, between the threads. The power loom will not have this much gap. The hand loom will have. So we would like to bring all data into similar pattern and then label the data and then train a classification model. That's what we try to do, to identify whether it is a hand loom or a power loom. If you are interested, right, I can get that project even now, but we have to execute it for free. Telangana, there is a board, textile park. Yeah, textile park, some textile park. The CEO, I know that guy. So if we want, right, if we want to execute the project, right, I can get it. Let me know if you have time. Okay. So that is about DBSCAN, and let us move on to anomaly detection. Now we have seen a little bit of anomaly here, right? Anomaly means a data point which have got a different pattern than than the other records. Right? That is anomaly, right? Anomaly is always not bad. I would say anomaly is always not bad. If you take the current society, the true politician, the uh, genuine politicians, are the good ones, are anomaly now, right? So anomaly is always not bad. Okay, so I'll take an example of that and try to explain. So code we'll see tomorrow. I'll show the theory today. So we need to do credit card fraud transactions. Okay, whether a transaction is fraud or not, we need to identify. So in the data, there are we have one data set in the Kaggle, and we are going to work with that. So there are 2,84,807 records in the data, total records. Okay, out of which 4,492 are anomalous. Okay, 4,492 are anomalous. Right? These are the fraud records. Out of 2,80,000, 84,807, 492 records are fraudulent transactions. Rest all are not. Right? Is this a classification problem or regression problem? If you look at this data, there are x1 to xn, some inputs, and there is y. There are zeros and there are ones. Is this a classification problem or regression problem?
Classification.
Classifications.
And out of the classification problem, did I label it properly? Did I label the data set properly?
Don't know. Maybe or may not be.
No, there is no. This is, yeah, please, you should say yes or no. Third answer is not there. Did I label the data set properly or not? So let me ask you a question. If I change all these ones to zeros to ones and ones to zeros, will the model work? Will the model work, or where will we get the problem?
Yeah, minority one, right? We need to check the minority.
Minority, you should give one. Rather, right? Rather, the precision recall scores also show you 99. So if you y cap, if you predict all zeros, how much accuracy you get on this data set? All zeros on this data set. If you predict all zeros, how much accuracy you get?
100%, sir.
No, not 100%.
All zeros, right? Here, 99.83.
99.83% accuracy you get. Because what is the accuracy score? How many are correctly predicted? That's the accuracy score, right? So out of
Yes.
total 2,84,807, 2,84,315 are correctly predicted. If you say all zeros, predict all the zeros, right? So 99.83% accuracy you get if you predict all are zeros. This is the, in classification class, right? We spent a lot of time understanding this, right? So when you are solving problems like these, that theory is going to be very useful. Okay. So, and one more thing, right? If you don't label the data properly, all the, here, these are all non-fraud records and these are all fraud records. If the intuition, right? Generally the intuition goes like this. All the non-fraud records should be given 1 and fraud record should be given 0, right? General intuition goes like that, right? If you give all these 0 and all these 1, the accuracy score also going to be 99.83. Precision is going to be 99.83. Recall is going to be, F1 score is also going to be. So your model looks like it is working. Whichever algorithm you take, it looks like it's working, but it is not working because mostly the model may predict zeros. On a data set like this, normal algorithms, right? Normal machine learning algorithms may actually fail, may fail. It is not that they will fail, they may fail. Okay, I'll show the whole, code example tomorrow on this data set, right? So this is the data set we are going to solve. So there are this many records and only 492 are anomalies or fraudulent records. So anomaly detection is a big problem in the industry, especially in manufacturing industry. When they manufacture maybe 100 bolts, maybe 1,000, maybe 10,000 bolts, maybe 1 or 2 may fail, right? So you need to find out that predict the failed bolt. So if you give the minority class 1, the precision and recall scores will actually focus more on this area and show you the error. Okay. So now what we should do is, I am actually talking about an approach called as Gaussian approach. This is not an algorithm, right? This is an approach. This is not an algorithm. This is an approach. So let us see what's that approach. So in Gaussian approach, to find out the anomalies, right? Anomaly detection using Gaussian approach, what we do is we split the data like this. We take all the 0 records, right, and take 60% of it as train set. Okay, Generally, when we are splitting data into train test set, right, we were taking some part of the zeros as train set and some part of the ones as test set. But here in Gaussian approach, we took only 60% as the train set. Okay. And the remaining 40%, we splitted that into 2020. And the one records, right, 50%, 50% we split it. One records how many? 492, right? When you split it into 50%, 246 and 246, right? These 20% are going to be 56,863, right? So in the cross validation data set, we have got 56,000 around 800 900 odd, and then test set also 56,900 odd number of records we have got. On the train set, we don't have any record belonging to one. Okay. In the train set, we don't have any record belonging to one. Okay. So now I take this 60% data and try to find out the sigma and the mu of each column. Right? Mean of this column, standard deviation of that column. Mean of this column, standard deviation of that column. Mean of like that. I am going to find means and standard deviations using train set. That's it. I'll use the train set to find mean and standard deviation only. Okay. Then I'll use that mean and standard deviation. Right. We can use. So I'll talk about this later. Right? Normal. So we take a normal distribution probability density function as the equation to predict the probability, okay, of each row. So I have mean and standard deviation of x1, mean and standard deviation of x2, mean and standard deviation of xn. So let us take the first row, right? First row, I need to predict probability of first row. Okay. So to predict probability of first row, this is how I am going to do it. So x superscript 1 is going to be row. Subscript 1 is going to be column. Okay. Probability of x1 1. Probability of x1 2. That means probability of this number, this number, this number, this number, like that we are finding. To find out probability here, using this formula, we need mu and sigma, which we calculated from the train set, right? So I'll take that and calculate the probability of row 1 to row m. All rows I'll find. Okay, so like this is the formula. So probability of x1 is going to be 1 by sigma 1 2 pi exponential of, right, mu 1 by sigma 1, mu 2 by sigma 2, mu n by sigma n, like that. So same standard deviation, same mean we are using, right, which we found out in the train set. Okay, now we have probabilities of all the rows, right? So there are two ways actually to find out whether a record is anomaly or not. One way is that you look at the range of the probabilities which belongs to this 60%. For this record, there is a probability. For this record, there is a probability. Like that for this 60% records, there is probabilities, right? There will be a range. It may start at 0. For example, 0.2 to 1, or maybe 0 to 0.2 range, right? Beyond 0.2 range, mostly it should belong to 1, right? Greater than 0.2 probability, record should belong to 1, because most of the data's probabilities, most of the records which are belonging to 0, the probabilities are within 0 and 2.2. Right? I can actually think that greater than 0.2, the record should belong to 1. Okay, that test I can do using the cross validation and test set. Right? I can do the test on the cross validation. If it is okay, then I can test it on test set. If it is okay, then I can use the same threshold. 0.2 is the threshold we found by looking at the probabilities on the train set. Right? We can use that threshold and make predictions on the production. Okay, there is another approach. That approach is you take the cross validation data and find out the probability ranges, right? which range, it is 0 records are falling and which range the 1 records are falling. Use that threshold to predict on the test set. So we have this code example on the website. Anyway, tomorrow I am going to explain that completely. So this is the credit card fraud detection is there. This is not magnifying. Give me 1 second. Approach is written somewhere. Oh, this is smart. Okay. This is the one. See that? Fit the model P of X on train set and cross validation set y is equal to 1 less than epsilon greater than epsilon. That epsilon is the probability where that the 0 records are falling. So the train set is used to find the means and standard deviations and the probability range in which the 0 is actually falling, and we'll test it on the cross validation set, and if it is not fitting well, right, then we'll adjust that probability on the cross validation set, use that on the test set and predict and see how it's working. If it is working well, then we'll use the same on the production also. That is a Gaussian approach of finding anomalies. Any questions here?
So this is also kind of classification, right?
Yeah, it is also classification.
So what is the difference between the actual classification?
There we are actually trying to derive an equation by passing the data. But here we are trying to look at the probability distribution and then trying to find out the predict the probabilities. In logistic regression, the equation will spit out a probability, right? We ultimately, after training the model, when you pass a record, the equation will give you probability, right?
Yeah, classification, the end product or end result is the probability, whatever the algorithm we take, right?
Yeah, here also the probability, but the equation we are taking normal distribution density function. But there is I'm going to answer that in a different way. If you know the data distribution, right, the density function of this data, right, the prediction is going to be more accurate than your logistic regression. Sometimes we know the probability distribution of the data, right? Did you get it?
No, sir.
This is manual. This is manually we are trying to do, right? This is manual approach, not automated. No, still no.
Actually, I did not get Shishram's question. Can you please repeat the question?
சொல்லவே மாட்டான், இவன் கூடவே சுத்தின்னு இருப்பான். ஆனா வாயே திறக்க மாட்டான். பின்ன ஆனா இவன்
Yeah, please. Sir, I think your question is not understood by Girigar, I think.
So my question is, so in this anomaly detection also we are trying to do the classification problem,
Yes.
address the classification problem.
Yes.
So We already have the classification, I mean the algorithms for the classification problems.
Okay.
And why it is a different approach to do the same?
Yeah, why are we not using it, and why is this different from the
Why we are
existing?
naming as anomaly detection and separate all the
Yeah,
stuff.
when you have this kind of data, generally the machine learning algorithms may not perform well because there is a minority data here. The algorithm's focus is always going to be on the majority data, and it may ignore these four. If you take the magnitude here, 2,84,807 total records and 492, right? It is 0.17 percentage, right? If you try to feed this data to machine learning algorithm, it may ignore. It may ignore. It is not that always you have to go with Gaussian approach. If the algorithm is ignoring these records and predicting 0 to all the records, right? That's not good, right? So we have to find out a way, right? We have to find out a way to distinguish between the 0 records and 1 records when you actually give input data, right? So if if those algorithms are failing, then we should come out with an equation, right, with a probability density function that explains that explains this data's probability, and use that probability density function to predict each record's probability and find out the threshold where the 0 records are falling, and using that threshold you actually can make predictions on the 1 records. It is for the data which is very tough to understand for the machine learning algorithms, the Gaussian approach. Got it? Did I answer?
Yeah, I'm just trying to understand. So you mean that we need to first apply
Yes.
the classification algorithms first?
Yes. Yes.
So
If you look at this code, right? This was done by Hanumantrao, one of our old students. He would have tried, he would have tried all the algorithms. He tried all the algorithms, random forest, all the algorithms he tried, and they are actually working similar. Yeah, please. I think you are asking something, and I interrupted.
The same one, sir. Like we need to try all the classification algorithms first.
Yes, sir.
And then if we are not able to, determine the accuracy, or we find some problem,
yeah,
then we may go to.
I'll answer this in a different way. In a data science team, there must be a statistician or a mathematician. If the problems are very tough like this, the mathematician or the statistician's responsibility is to generate a mathematical formula or a probability, the density function that understands the data pattern. Using that formula, we should be writing the code to identify the threshold and then building the model. This is for the toughest problems. Got it?
Okay. So in classification problems also, we are actually giving, giving one to the minority data set. Still,
yes.
They won't predict properly.
Giving one to minority data set makes the metric work better. Metric work perfectly, right? Metric means that precision recall F1 score, the numbers outputted will be appropriate. To make the metrics work appropriately, we are giving 1 and 0. That's not going to improve the algorithm's power, right? Algorithm's capability of understanding data, right? Got it?
Yeah.
Algorithm's capability lies in the number of iterations, the stochastic gradient descent, the way it is finding the thetas. That is all, that is all the capability of the algorithm. Right? That capability may not be sufficient to understand this kind of minority records. You will understand the problem only when you take the data set and start working on it. Now, this weekend, definitely you should, all of you should attend on Saturday. and do the practice on this data set. This is a really important, very important data set for industry, and in many interviews they will ask. In many interviews they'll ask if you are fully equipped with this, right? You can, you can actually answer for half an hour to 40 minutes. They can do interview on this particular data, this kind of data. Got it?
Yes.
If possible, right, start working on this data set from today. Right, look into DBSCAN a little bit. Right, try to experiment with it today, tomorrow, and maybe day after tomorrow. Start working on from Thursday. Start working on anomaly detection, and Saturday, Sunday also you should work on it. You will get full grip on total machine learning, total process, overfitting, underfitting. All the concepts you will get full grip on if you practice this one data set. Got it? I'll stop here today because I mixed up.